So my name is Biao. I'm from Alibaba Cloud. It's my honor to be here to give everyone this presentation in this year NSDI. My topic is Poseidon, a consolidated virtual network controller that manages millions of tenants via config tree. It's deployed in Alibaba Cloud for more than 3 years, and it's co-work done by Zhejiang University, Alibaba Cloud, and Tsinghua University. So let me first give a background of this topic. How does people configure cloud through a controller? Actually, the users will leverage all kinds of cloud control API. So for example, create VPC, create VM, create a route, and create a load balancer. But what happened behind that is there is a virtual network controller that takes all these APIs and process it and make all kinds of installation on different devices, such as our virtual host, virtual gateway, and even physical devices. Then how does the controller work in this case in a large-scale production environment? So majorly we can divide this into 3 steps. First, they receive the API. Second, they try to calculate what change they need to install on these devices. Then they try to configure all these devices. In specific, we'll dive into the second step because that is the most complicated part. The reason is the service and the cloud network is really complicated. In this case, I'm showing you a virtual machine, which is a very simple object, but a VM can belong to a VPC. A VPC has its own routes, route table, ACL. It can connect to the other peer VPC. This VM might have its own private IP and an elastic IP. So all these kind of things, they form a very complicated dependency tree. The first thing in the calculation, we need to identify all the dependent configs so that the second step, so that it tries to do all kinds of SQL and if-else in the logic to find out all the dependent configs. Second, it tries to locate what devices this config should go to. Should it go to host A or host B? Should it go to virtual gateway or virtual gateway 2? So the second thing is try to locate all the devices. The third is calculate config changes which we should install on these devices. You may wonder, why do we need to calculate? It's very straightforward. There are VM and VPC that just install it. That's because on these devices, you might have some existing dated config on top of them. For example, this gateway might have already the ACLs for VPC A. In that case, you need to do an update operation instead of install new. So that calculation is also a key here in the step 2. This kind of workflow is happening in the cloud scale every minute, every second. So which brings us to 4 challenges right now facing this kind of scale. The first challenge is performance degradation due to longer search chain and the table size. So by the years past, the cloud service has improved a lot. We have introduced different services, NAT, load balancer, and acceleration services. All these services add up to the complicated tree, making the tree more and more complicated. You have to do a longer search layer. The second thing is single network, the scale is also growing up. So which means you check your database for your SDN controller, the data table entry grows from maybe 100,000 to millions, and right now even reaching 1 billion entries in one database. All these will add up to your service SDN controller processing time. In our observation, the P99 latency for the past 5 years has almost doubled, which is really a good degradation for all of us. The second challenge comes from the rapid growth of workflow. So users love cloud. They create all kinds of things on the cloud. Their VM, their apps, their network resources. The more resources they create on the cloud, the more frequent they will try to invoke to manage them. According to our observation, we are seeing a steady growth of the API calls, reaching right now more than 10 billion calls per day, a single day. That is really insane. The second thing is a scale of a single VPC, which means a tenant created VPC in 10 years ago, it might only put it might put only 10,000 VM or 5,000 VM in one VPC. But nowadays, people can create more than 1.5 million VMs in one single VPC, which means right now, if you try to update a route for a VPC, it might have to send to more than 10 times of devices compared to 10 years ago. This also makes the processing time much slower. The third thing is cloud-native apps. That is an interesting point. Why cloud-native app is a challenge? So we love cloud-native app because it can give us a lot of scaling benefit. You can scale very easily, but the cloud-native app scales well because of the controller can provide resource easy for them, which means compared to the console-based network management, people usually wait for 1 or 2 seconds for the controller to finish their job. But for a cloud-native app, they will not wait for 1 second. They will wait for only 100 minutes for this app to scale when the peak comes. So there are two examples. For example, in China, we have some e-commerce business. Then one day, for example, Black Friday, right? Black Friday. At that time, a lot of people will try to shop on your website. In this case, you have to scale instantly for a lot of resources for the cloud-native app to respond. The second thing is those social media apps. When there's a hot event suddenly happening in the network, then people will start trying to click the app, and that will generate 100 times more traffic than before. And then the cloud-native app will try to scale, and it scales by asking controller, hey, give me more bandwidth, give me more reports, give me more NICs. The third challenge comes from the code redundancy and OpEx. So in the beginning, in order to make the network service more flexible, we develop different controllers for each individual service. That is good for every service to develop by itself. But by the years, we have more than 50 controllers individually for different services. That introduce a lot of code redundancy and OpEx. So that's all the challenges we were facing. So right now we are trying to solve it, and our solution is Poseidon. It has two major goals. One is to improve the performance, especially for API throughput and the latency. The second is reduce OpEx. So in summary, it has three key designs here. We call AAA. So the first thing is architecture. We partially consolidate the common modules of separate controllers into a unified Poseidon controller. The second thing is do abstraction. We propose a service and device-independent abstraction to unify the management of heterogeneous devices and diverse service APIs. The third thing is to add acceleration. To accelerate the config change calculation, we design a tree-based config change calculation logic. So in the following slides, I walk through each of them. The first design is the partial consolidation architecture. First, I will give an observation here. As we know, just in the beginning, we divide the cloud controller workflow into 3 steps. The first step is to process all kinds of cloud API. But the cloud API is bound to different service. So VPC service and the load balance service, they will have different verbs. They will have different parameters. So that part you cannot unify. It just goes with different service and evolve. The second thing is the config change calculation part. That part we can somewhat express in a similar logic. The third thing is device configuration. Device configuration, for device itself, it might not change as frequent as service, but still updates. So according to this observation, what we choose is that we will leave the cloud service part to each service team. They will do whatever they want and iterate as fast as they want. But we will consolidate the configuration change calculation and device configuration part into a single platform. So reduce OpEx and make sure the thing will not be redundant. So the picture is the architecture we finally get. We partition the control plane into 2 layers. The service-related layer for processing APIs and meeting the service requirement, tenant requirements. The second part is service independent layer. That is for calculating and pushing config changes. In addition to that, we also design a unified agent on heterogeneous devices to translate unified config changes to underlying primitives. In this case, it gets both flexibility and avoid code redundancy. The second design is treating abstraction. So first of all, we classify the object in controller into 3 categories: service, config, and the devices. For service, we have already left it alone to go with the service team, so we will not try to unify it. But config device, these 2 objects have to be unified, otherwise the architecture cannot work. The other thing is the actions. We also try to summarize what kind of action we will do in a controller against the device and the config. Finally, we need to do a create, read, update, and delete, and then install. And then what we choose is that we will abstract config, device, and their relation in a unified way. So what we get is that we define 3 basic objects, which is very straightforward: configuration for configuration, device, and the device group. We also define 5 atomic operations: create, delete, update. These 3 is straightforward. I will not spend time on it, but the interesting part is relate and unrelate, which is rare to see. As I talked earlier, the devil lies in the complexity. So the relate, we have three kind of relation: conf and the conf relation, conf and the device relation, the device and device group relation. With this kind of denotion, we can simplify all the complex dependency in the network in all kinds of relationship. So we can do the translation in a unified way. Sorry, to catch up the time. So after that, we can transform the code from SQL and if-else and Java, Python to unified 5 atomic operation over 3 basic objects. That is very key because of that, we can do all the following stuff. The third design is to accelerate. So with the trading operation, we can form multiple device group conf trees. What we call it is called a trading tree, just like this one. So in a trading tree, the device descendants imply all its required confs. Configuration update means that we need to calculate what have changed in its tree and then try to find out changes and send to this device. But it would be too naive to try to calculate all the trees one by one from root to every node, because if a VPC has 1.5 million nodes, you cannot scale, you cannot do a naive traversal for all of them. That would take too much time. So we try to answer this question. We define the problem is whether a conf is a descendant of a device or not. So naive traversal is not working. So what we have here is that the descendant relation is transitive from parent to child. This is very good for us. We leverage this property and use it in our algorithm so that the complexity will get lower and we don't need to travel from the roots. So first of all, let's try to use the reference count to denote the descendant relation between a conf and a group. We have tried 3 kinds of algorithms. I will not spend time on it because of time. So we tried all based way, which is good for deep tree. We tried some based way, which is good for wide tree. But finally, we get a function based, which is kind of is 0-1 based conditionally function way to calculate the reference. It's similar to sigmoid or some machine learning algorithm. But anyway, so this works, and finally we get a good result. And this platform has been deployed in Alibaba Cloud for more than 3 years, and we have some evaluation. First of all, the throughput and the P99 completion time has improved by 21 times and 4.4 times. And we do some test bed against the other top 5 vendors in the concurrent API processing time. We can observe that it is in the same test benchmark in the test environment. We are 1.8 times to 55 times faster than the other top 5 vendors. We also reduced the line of code a lot, at least 22%. At the most, it will be 41%. So Also, actually, I want to share some experiences when we are doing the Poseidon, because it's like changing the engine while a plane is flying, because there is already a very large scale old SDN controller, traditional southbound, northbound API. That controller has been running there for many years. And when we develop Poseidon, we have to migrate from the old controller to this new one. It's very challenging. We cannot break the service. We have to continue provide the API to our customers. That is the first experience we have learned a lot. There are more details in the paper. The second thing is that we also do we also have some real stories when there are some extreme situation. When I say extreme situation, I mean, for example, a very large data center just get outage, and when it resumes, you will get a lot of the BGP signal back, and you have to recalculate all the routes and configurations. If you are using an old controller, that will take minutes or hours, but in Poseidon, it finishes very fast. It saves a lot of time and really saves our customers. That's it. I think the summary is that we demonstrate the challenge and the issues, and we design this architecture and did a lot of deployment and achieve some results. And that's my presentation. Thank you very much for your listening.